Hello, welcome to the first lecture on microprocessor and microcontroller. So today we will start with the 8085 microprocessor, and in this lecture we will be dealing with the internal architecture of this particular processor. Okay, now before going into the specifics of the internal architecture, let's have a brief outline regarding what this processor is. So our 8085 microprocessor. So it was developed and marketed by Intel in the 1970s. Coming to the technical specification, it is a 8-bit processor, right? That means it had 8-bit registers for data handling. Its ALU had 8-bit capability, and the width of its data bus was 8-bit. Okay. It had the capability of handling up to 64 kilobytes of memory. 8-bit word, 64 kilobyte memory. Okay. So 65 kilobytes of memory means it could handle up to it could address up to 64 kilo space, 64 kilo locations, let's say address location. It means it could handle 2 to the power of 16 locations. That is, it had an address length of 16 bits. So it had a 16-bit address, 8-bit word and 16-bit address. Coming to the physical aspect, it had a 40-pin DIP. DIP is a dual inline package, right? The chip that you see like this. Something like this. This is a dual inline package. That is, it will have legs on or leads on both sides. That is a dual inline package. Okay. Most modern processors are not like this. They come in a different form factor. It had a plus 5 volt power supply, right? Plus 5 volt means actually, in fact, this 5 of the 8085 comes from the fact that it uses a 5 volt supply. Earlier processors used a 12 volt supply, and it had a 3 megahertz clock. So all of these terminologies you should be familiar with, the word length, address, clock and all, because I am assuming that you have already taken or you have already gone through your previous computer architecture or computer organization course, and you have at least brushed up your basics. So even in the future, when I'm taking this lecture, I will be assuming that you know some of the foundations which you have learned from that course. Okay. Now before going into the architecture, or let's start with the architecture. Architecture of 8085. So when we are talking about architecture here, we mean the internal architecture and the internal components. So the main components that are there are some elements within the processor which will group into certain parts. So first ALU, then there are the registers, then there is the internal bus, timing and control. Interrupt control and serial data control. So some of these we'll be seeing in detail, and some of these we'll just go through, we'll just brush through, because the very details explanation of some of these are not within the scope of this course, right? Okay, now let's start with the first element, which is the ALU, arithmetic and logic unit. So at this point you should be knowing what ALU is, because you have designed, you have learned about it in your previous course. So arithmetic and logic unit used for performing arithmetic and logical operations like addition, subtraction, and or shifting, things like that, right? And here this it is called as an accumulator. We will see about it in a little bit details once we deal with the registers. Okay. The same thing goes for flags also. It is also a register, which we'll be dealing with later. These two, ACT and temp. ACT stands for accumulator temporary register, accumulator temporary register, and TMP is just temporary. So the main thing about these two registers is that they are not accessible by the programmer, not accessible by programmer. That is, they are hidden registers. Hidden. Okay. So the purpose of them, their purpose is to make the functioning of the accumulator smoother. So like in the complete architecture, we will be drawing that the data lines are directly connected to the ALU or something like that, or from the accumulator we are directly giving to ALU. Sometimes we draw like that, but it is not like that. There is always a buffer sort of or temporary register in between, or which is directly connected to the ALU. There will always be some sort of temporary register, that is accumulator, temporary and temporary. And the thing is that we can write to the something to the accumulator temporary and temporary, and from that the ALU will take the data and it writes back. Okay. It writes back to the accumulator or to the data bus. This is the data bus. So from the data bus it may come back to the accumulator or accumulator temporary or something like that. Okay, so that is it. The same thing comes for temporary also. So flag registers, we'll see them in detail. Anyway, just understand that whenever an operation is carried out by the ALU, if it is almost certain that some of the flags will be affected. Okay. Okay. Now let's talk about the registers of 8085 registers. The registers, so these numbers written besides them, these are the length or the size of the register. So if it is written 8, it is an 8-bit register. It is written 16, it is a 16-bit register. Okay, so why are some registers 8-bit and some registers 16-bit? Like I mentioned before, 8-bit is the word length of the processor and 16-bit is the address length. So 8-bit registers are used for data handling and 16 bit registers are used for address handling. Okay. The other thing is that what if even the way these registers are drawn, what if we put together two, right? What if we put together B and C, and we put together D and E? Similarly, what if we put together H and L? So they are called register pairs. This is a BC register pair. Similarly, DE register pair, HL register pair. Okay, so these can be used as what? 16-bit registers if you want for some purpose, right? So these 6 registers, okay, B, C, that is, let's change the color, B, C, D, E, H and L, they are called general purpose registers. Okay, general purpose registers. The name is pretty self-explanatory. I don't think I'll have to explain that. So whenever once we're talking about general purpose registers, there is obviously special purpose registers, right? General purpose registers are there, then again special purpose registers are also there. So if B, C, D, E, H and L are the general purpose registers, which are the special purpose registers? We have a stack pointer, program counter, accumulator, and our flag register. Okay, we'll cover each of these one by one, don't worry. And the last point in this part is that yes, these are general purpose registers, but out of this HL is sometimes used as or the HL pair is used as a data pointer, right? Data pointer. You should know what a pointer is. It is something that is used to store data, store an address, right? Pointer means it points to some memory location, that is, it is used to store the address of something. So data pointer means suppose we have some data in the memory and we want the address to it for some sort of purpose. We want to store the address of that pointer for some operation. Then what we do is that we take this HL pair, 16-bit HL pair, as a data pointer, and we use that. Okay, for example, if the say the address is FF12 hexa, and you store it in the HL pair. Okay, you store it in the HL pair. So once you have it there, you can just refer to the HL pair. You don't have to write this whole thing every time. That is an inefficient way. So that is what HL pair is used for, as a data pointer. No other registers are used as data pointers. Only HL is used. That is in fact a special purpose of a general purpose register pair, let's say. Okay, now we'll talk about the flag registers. So flag registers or registers, flag register. Okay, only one is there, flag register. So flag registers contain flags. So what are flags? Flags are single bits, ones and zeros, single bit. Each one bit is a flag. Okay, here this is a flag, this is a flag, this is a flag, this is a flag, and these are separate flags. So what are they used for? They are used to denote the status, denote some sort of status. It depends on which flag it is, what status it is. Okay, so let's and these are empty slots. Okay, this one, these are this is empty, this is not used for anything. Okay, why they designed it this way, I don't know. Anyway, so the first one is S, which is a sign flag. Okay, so all of these flags are set once an operation is carried out by the ALU and a result comes out, right? And every time a result comes out, depending on how the result is, these flags may change or they may not change. Certain operations trigger a change in all of the flags. Certain operations trigger an change in some of the flags. So it depends on the particular operation which of the flags are affected. Okay. So sign flag, it shows the sign of the ALU output. ALU output. Okay. So it is a bit, right? So it can be either 0 or 1. So if the sign flag is 0, what does it mean? The output is positive. If the sign flag is 1, it means the output is negative. So you might be recognizing this because this is how the sign bit of a 2's complement or a sign magnitude form number worked, if you remember from your previous course. This is the same thing. So whatever is there, whatever is the sign bit of the result, that is directly taken into the sign flag. Okay. Now the next one is 0 flag. So it shows whether let's say shows if ALU output equal to 0 or not, right? Whether ALU output is 0 or not. If the sign flag is reset, not 0, sign flag is set 0. What is here? What does it? Not 0 means ALU output is not 0. If sign flag is 0 flag is 1, it means the ALU output is 0. Okay, depending on whether ALU output after an operation is 0 or not, this 0 flag is changed. The next one is parity, P, parity flag. Okay. So okay, let's take a new page to explain that. Parity flag. Parity. So let's discuss the concept of parity first. I don't know if you know this or not. So suppose let's take a bit string. Okay, 1 0 0 1 0 0 1. Okay, 1 0, 8 bits. So now how many ones are here? 1 1 1. So 3 ones are here. Again 1 0 0 1 0 1 1. Here 4 ones, right? So parity is this is parity. This is called as an odd parity. This is called as an even parity. That is just checking whether the number of ones of the output of the ALU is an even number or an odd number. Okay, so it depends on the processor whether they want to implement even parity or odd parity. So here for parity flag, we are using even parity. That is, if the output is 1, sorry, if the parity flag is 1, it means that the output satisfies even parity. That is, ALU output has even number of ones. Okay, ALU output has even number of ones when the parity flag is set. If it is 0, ALU output doesn't have even number of ones. When it is 0, it is not saying it has an odd number of ones. It is saying it doesn't have an even number of ones. So obviously it will have an odd number of ones. The thing is that here the processor is checking for even parity, right? It is checking for even parity. It will only say whether it has whether the number is, the output of the ALU has an even parity or not. So if there are even number of ones, it will say okay, fine, it is set, it has an even parity. So the other thing is that it doesn't have an even parity. It implies it may imply that it is having an odd parity. Okay. So the next flag register is CY, which is carry flag. Okay, this is to denote whether a carry has occurred. Carry occurred during ALU operation. 0 means no carry. Right, so where does carry occur? Suppose we have an addition, say 1 0 0 1 0 0 0 1. We want to add it with something like 1 1 1 0 0 1 1 1 1 1, something like this. So anyway, we do some additions, and finally when these two are added, it will be something 1 0 or 1 1 0. So this bit, it is a 9th bit. That is a carry is generated, right? Or an overflow is occurring, let's say. But here, since we are using it for addition or some purpose like that, we are saying a carry is generated. So that is the carry flag. Carry flag is set whenever this is generated. Carry flag is set. You cannot, I don't think it is better you call it an overflow. It's better you call it a carry. So carry is generated, and if a carry is generated, the carry flag is set. Otherwise, the carry flag is not set. So the advantage is that even if you are doing an arithmetic operation and you are getting a 9th bit as a carry, it will not be lost, because if there is a carry, that will be stored in the carry flag. So you can access it and you can use it. Okay. So the last one is, let me just remove this. AC, which is auxiliary carry. Auxiliary carry. Again, if it is 1, then auxiliary carry occurred. If it is 0, no auxiliary carry. So what is auxiliary carry? Here for carry we considered what, the 8-bit addition, right? So suppose the addition is like this, and something plus something, and in the result there is a carry from this bit to this bit, that is from the 4th bit, or if you are assume this as the 0th bit, 0 1 2 3, 3rd bit to the 4th bit, then that is called as an auxiliary carry. That is, if there is a carry from the lower nibble to the higher nibble, then it is called as a auxiliary carry. Okay, so let me just go through the flag registers, flag bits once more. Sign flag to denote whether the output or ALE output is positive or negative. Zero flag to denote whether the ALE output is 0 or 1. Then parity flag to check if there is an even parity or odd parity. Carry flag to check whether to denote whether there has been a carry from the 8th bit or 7th bit outwards or not. Then auxiliary carry, which is to denote whether there is a carry from the lower nibble to the higher nibble. Okay, now let's consider the next one, stack pointer. Stack pointer. So before that, what is a stack? What is a stack? Stack is a last in first out data structure. Okay, LIFO, last in first out, last in first out. I hope you are familiar with this because we have dealt with this. In fact, we have dealt with stack pointer itself in our previous course. What is a stack? Again, stack is something you are arranging. You're just putting data like one by one. If your stack starts here, you just keep on putting data here. You will keep my data on top of it. Again, you will put a data here like that. Just keep on putting data on top of each other, right? Like you're keeping a stack of books, you see, right? You keep one book on top of the other. And if you want to remove, you will have to take from here. So you just take from here, then you take from here, then you take from here, like that. That is, you have to add from the top, you have to remove from the top. And these operations are push and pop. Pushing is you are adding, insertion. Popping is deletion. Okay, you are inserting, it means push. You are deleting, it means pop. That is the terminology used for stack. Okay, and stack will have two things. You will have a bottom of stack. Okay, you will have a bottom of stack. That is obviously to denote from where the stack is starting, the bottommost point, and then you will have a top of stack. Okay, you will have a top of stack. So this bottom of stack, it is a static thing. It is static in the sense, okay, you already know, okay, once you know where the bottom of stack is, you don't have to keep track of it because it won't change. It is always there. But this top of stack, it is dynamic. It is dynamic in the sense that as pushing and popping is done, the top of stack changes. So you need to keep track of the top of stack. That is what a stack pointer does. It stores the top of stack of 8085 stack. So in 8085 processor, we assign certain areas to be the top of stack. We assign, okay, we say that, okay, this much area in the memory is top of stack, is stack, and we say that, okay, the base address will be stored, it is stored somewhere safe. So that is known. So what you have to do, you just have to keep track of the top of stack. That is what stack pointer does. It just keeps track of the top of stack. And just a reminder, what is a stack used for? In general, you can just push and pop, but what is the purpose of just pushing and popping? Usually it is used for storing data before executing a routine, right? A routine is something like a function that is the normal flow of execution of the program is happening, and you just have to go to some other area, do some execution and come back. So at that point, once a routine is called, all the temporary data which are in the registers, flags, accumulator, things like that, they are stored in the top of stack, right? They are pushed into the stack. Okay. We had earlier we had talked about the flag bits, right? And we had so we have our flag bits, flag register, and we just add our accumulator. So what is an accumulator? Accumulator, we call it as A, and we mentioned that it is a special purpose register. So accumulator is 8085 is an accumulator based processor. Why? Because most of the instructions which need the ALU, that one of the operands many times have to go through the accumulator, right? So it is heavily dependent on accumulator to store at least one operand. That is there. So for regular ALU operations, then if you are doing some sort of data transfer with the input IO device, input output device, that is also going through the accumulator. Okay, whatever data transfer is happening between the input output devices, that is happening through the accumulator. So that is the main two functions of the accumulator, and accumulator is also a 8-bit processor. Okay, now you might be wondering why I have drawn like this. Okay, flags we have gone through, accumulator okay we are going through now, then why am I drawing like this? This combined is called as a program status word. Okay, program status word. Flags plus accumulator is called as program status word. Okay, now let's come to our last two special purpose registers that we'll be dealing with. That is the program counter and instruction register. So I'm taking these two together because they work in sort of unison. So as you know, the program counter always program counter, or I'll just write PC. Okay, program counter points to the next instruction to be executed, right? Program counter points to the next instruction to be executed. So here suppose the program counter content is 2005. Okay, the program counter is having 2005. So through the bus, address bus, it transfers that data to the memory. And here what is happening in 2005, there is some value. So it is taken through the bus again. It is taken through the bus. This is the external bus, right? And it is given to the internal bus. Again, you know what a bus is. It is just some parallel lines which are used for data transfer. External bus is there, internal bus is there. And you have learned this separately. Data bus and address bus are there separate. Address bus is used to transfer address, and data bus is used to transfer data. And address bus is always unidirectional, and data bus is most of the times it is bidirectional. Okay, so through the external data bus, whatever content is there, that is, we are assuming this is an instruction because we took it using the program counter. It is coming through the data bus, external data bus, and given to the internal data bus. Okay, and once it reaches the internal data bus, it is taken to the instruction decoder. Actually, it is not just instruction decoder, instruction register IR, instruction register program counter. Okay, IR is there. It is given to the instruction register, and from the instruction register it is given, but it is stored in the instruction register. From the instruction register it is taken to the instruction decoder, and okay, it sees okay what all are there and gives the required data to the control unit, and everything from there, everything is, you should know what the how program counter instruction register works by at this point. Okay, so I'm not going into detail regarding that. Okay, so that is regarding the main components of this internal architecture. So let's put everything together. Okay, so now we have put everything together. So till now what have we learned? We have learned about the accumulator, right? We have learned about the flags, the ALU, the instruction register and instruction decoder. We have learned about the registers. Okay, there are some elements here that we have not explained in what you say explicitly, but we will do that in the future. Okay, this is just a brief idea of what we are giving. Okay, then we mentioned regarding this interrupt control, our serial data control, and our timing and control, right? So, and also this what do you say, internal data bus. So these some elements are there. We'll do one thing, we'll stop the lecture here, and we'll take another lecture to explain this in detail. Okay, thank you.